Armature reaction. This creates considerable effect on the performance of alternator. So when we are going with the DC generators, the effect is somewhat lesser in the DC machines when compared to the alternator. So basically, we are using three kinds of loads, and we are connecting three kinds of loads in the grid or across the terminals of the AC generator, and we are calling it as alternator. So this, when you are connecting the resistive load across the terminals of the alternator, it withdraw in phase current from the supply, or it is withdrawing in phase current from the alternator terminals. So there will be no phase angle difference in between the voltage and current. And when you are connecting the inductive load across the alternator terminals, so that inductive load will withdraw a lagging current from the alternator that leads to some phase angle difference in between the generated EMF and the current drawn by the load. So that creates considerable effect on the system. As like this, that similar effect is produced by the capacitive load also. So what is meant by armature reaction and how it affects the terminal voltage of the alternator? The simple definition for armature reaction is the effect of main field armature flux, the effect of armature flux on the main field flux is called as armature reaction. The main field flux is produced by the current IF, and this armature flux is produced by the armature current IV. So whenever you are connecting the load across the alternator terminal, automatically the armature current will rise. And when you are loading the alternator, so this is the basic definition of armature reaction. And there are three kinds of effects are produced due to the connection of different loads with the alternator terminals. So one is called unity power factor. So at this case, we are connecting the resistive load across the terminals of alternator. And when the load power factor is zero lagging, it means that we are connecting pure inductive load across the terminals of the alternator. And when you are connecting pure capacitive load across the terminals of the alternator, so that creates load power factor is zero power factor leading. It creates zero power factor leading. So what is happening inside the machine when you are connecting these three kinds of loads: resistive load, inductive load, and capacitive load? So there are three kinds of effects are produced when we are connecting the three different loads across the terminals of the alternator. One is unity power factor. So it creates cross magnetizing effect. So this is happen when you are connecting the resistive load across the terminals of the alternator. And similarly, when you are connecting the inductive load across the alternator terminals, it creates lagging power factor load and it produces demagnetizing effect within that machine. So that demagnetizing effect reduces the resultant flux or the main field flux, and that also reduces the generated EMF of the alternator. Then when you are connecting capacitive load across the terminals of the alternator, the power factor will be the leading power factor, and there the generated EMF or the load current withdrawn by the capacitive load will lead the voltage by an angle. So if it is pure capacitive, so that current will lead the voltage by 90 degrees, so that creates a magnetizing effect, so that increases the resultant flux of the machine, and that leads to the increase in the terminal voltage of the alternator. So here you can see the images, and here there are two fluxes are shown. So one is shown as a dotted line, so that represents the flux produced by the armature current, and it is named as pi a. And here the another flux which is denoted by the green color lines, so this indicates the field flux. This is created by the appliance of field current if, and this is the this yellow line indicates the resultant fluxes of the machine. So based on that, based on the load connected with the alternator terminals, the resultant flux of the generator is varying. So based on that, the generated EMF is also varying. So this is the animation for the pure resistive load. So we are considering north and south pole, and this is the main field flux created by the field current IF, and this is the armature flux created by the armature current. And here these two fluxes, IF main field flux and EMF induced in the machine due to the flux pi f is represented by EPH, and this IAPH represents the armature per phase current and pi A represents the flux. So here you see that the two fluxes are displaced by 90 degree. So that produces the cross magnetizing effect within the machine. And next we can see the images and animations of the alternator when you are connecting the inductive load. So here this is the main flux produced by the current pi f, and armature flux pi a produced by the armature current ia. So here you can see that there is 180-degree phase shift in between the two. So this armature current opposes this armature flux pi a opposes the field flux, and it leads to the reduction in the resultant flux. So this is happened. This happened when you are connecting the inductive load across the terminals of the alternator. So the alternator effect produced by the alternator produces demagnetizing effect. And the next one is the when you are connecting pure capacitive load. So there will be that two fluxes are in phase with each other. So that will increases the resultant flux, and that leads to increase in the terminal voltage of the alternator. So this is called magnetizing effect. So these three effects is due to the connection of three different loads at the alternator terminals. Thank you.